than that, let's go ahead and do our f-test. The test starts with a hypothesis. Null hypothesis first will be that all the beta sub I in the regression are equal to 0. That means that no x in the regression explains the y. Clearly we can't answer the question about other x's out there in the world. Alternatively, at least one of the betas is not equal to 0. Alright, these two are complementary of events, right? Either they're all 0 or at least one of them is not 0. And if at least one of them is not 0, then at least one of the x variables in the regression explains the y. Alright, then with any test that involves degrees of freedom, we have to now calculate the degrees of freedom. The k has 2 degrees of freedom. It has k degrees of freedom for the top line and n minus k minus 1 degrees of freedom in the bottom line. So in our example, there are 2 x variables, so k is 2, n was 9 minus 2 minus 1, and that works out to be 2 and 6 degrees of freedom. We'll use the standard alpha of 5% and go to the f tables to find the appropriate value. Alright, so here's our f table. I note that we only have one f table and we have an alpha of 5% on this one f table as a standard alpha, and at this point we don't need to worry about any other alphas. Alright, so we have 2 and 6 degrees of freedom. The first degrees of freedom will be for the top line. The second degrees of freedom will be down the side here, so 2 and 6 degrees of freedom has a critical value of 5% of 5.14. Okay, so that's our critical f. Let's draw a representation of the f distribution. Alright, like the chi-squared, it starts at 0 and then trails off to infinity. Our critical value is 5.14. Alright, any calculated f below that in the regression is insignificant. Anything above and the regression is significant. Alright, so let's write a quick decision rule like that. If fcalc is less than or equal to the 5.14 critical value, the regression is insignificant. Alright, there's an insignificant explanatory power there in the sample. It means that there could be some in reality, but the sample data doesn't show up enough. Alternatively, if fcalc is greater than 5.14, alright, then we're far enough away from 0 and the regression will say is significant. There is sufficient explanatory power there in the regression to help us be useful for predictions and for explaining the y. Alright, the next step would be to do the calculated value, fcalc. So regression sum of squares divided by k divided by the error sum of squares divided by n minus k minus 1. Alright, and those values were given above. The regression sum of squares from the table Excel output 1.05632 divided by the k of 2, and that divided by the error sum of squares of 0.13524 divided by degrees of freedom there of 6, and that works out to be approximately 23.4, which is clearly much greater than our critical value of 5.14, so we'll just say simply for a decision that the regression equation that we have is significant. Right? In other words, the explanatory power that we have estimated is much more than just simple random noise would do, and so we'll assume that that means that this regression is statistically meaningful. Alright, the next step and the third thing that we'll do for the basic technical analysis is talk about a concept called R squared and its interpretation. Sort of analogous to little r in simple regression, and they are related. R squared is a measure of the strength of a regression. R squared is a number between 0 and 1, and sometimes it's done in percentages, so in percentages of course it'll be somewhere between 0 and 100%. Looking at those two extreme cases, much like we did for little r in simple regression, if r is 0, the regression explains nothing. And on the other end, if r squared is 1 or 100%, the regression explains everything. Well, actually not everything so much as all the variation in the y variable. Alright, the formula for r squared is simple enough. R squared is the regression sum of squares divided by the total sum of squares. Alright, remember that in the regression we're trying to explain the total sum of squares with the regression. So r squared is the proportion of the total variance explained by the regression. So for our example, we were given, and we took down the regression sum of squares and the error sum of squares to calculate the r squared that could work out the total, which is the regression plus the error sum of squares, that which is explained plus that which is unexplained. And those values were 1.05632 plus 0.13524. Let's add them. Alright, and I get on my calculator that that's 1.19156. Alright, we're ready then to calculate r squared. Again, let's write down the formula. so we don't put the wrong values in. Alright, regression sum of squares 1.05632 divided by the total 1.19156, and that works out to be 0.8865, or as a percentage 88.65%. Alright, the interpretation that we'll do always with an r squared, whether we calculate the r squared or whether it's given to us, is as follows. It means that this regression, being that the exact equation that I wrote down for the regression before, with those exact numbers and x variables, that this regression explains, alright, the value for r squared, 88.65% of the variation or variance, it doesn't matter which, we'll say variance, in the y variable, and let's not just say y variable, but in the particular y variable here, which is in the number of class 8 trucks sold. Which is not a bad value for r squared, but it's could be better. Alright, several things that we need to worry about to sort of clean that up, but that's the end of the technical analysis done in the reverse order. Alright, so to sort of tie up a few ends, in simple regression, r squared would just be our little coefficient of correlation, little r squared. Alright, going back to multiple regression, since both fcalc and r squared have sum of squares formulas, we can write our fcalc formula with either sum of squares or r squared. So the way I'd written it down before is the regression sum of squares divided by k divided by the error sum of squares divided by n minus k minus 1. Alright, and that also can be done as r squared divided by k, all that divided by 1 minus r squared divided by n minus k minus 1. Okay, and most students find that the latter formula is more convenient because of the order of the analysis that we normally do. Right, normally our multiple regression technical analysis, basic technical analysis, remember this is just the tip of the iceberg. We won't do any more here, but this is not all of it. Right, we'll first look at r squared and do as an interpretation as above. After that, we'll then do the f-test for the significance of the regression. And then finally, we'll do the t-tests for the significance of each individual x. Okay, and that's the way we would normally do it.